So in the 33rd lecture, the topic I'll discuss today is PN junction, or then we'll come to PN junction diode. So I'll start with PN junction. What do you mean by this PN junction, and what is a PN junction diode? Then we'll see the application of this PN junction. Now PN junction is nothing, it is simply, we say that a PN junction is formed by, just suppose you have a, this is a, I told you what is a p-type material and what is a n-type material here. P and this is n. Say this is p-type and this is n-type material. So we say that the PN junction is nothing, it is formed by combining a p-type, and a n-type semiconductor, in very close contact, This is called a junction formed here, a junction at this is called a PN junction overall. Now it is not simply, it is like, cannot be simply like this, that you take a p-type material and a n-type material and you simply join this and it becomes a PN junction diode. No, it is not like this. There is a complete fabrication process for this. So let me define this first of all. What do you mean by this PN junction diode? I say that this PN junction is formed by, let me define it first, is formed by combining a p-type semiconductor, a p-type semiconductor, of course having donor impurity, and n-type semiconductor which is having acceptor impurity, of course, in a close contact, I can say, in very close contact, So this is called a PN junction, formed. Now a PN junction is, or okay, let me one more point. I can say that a PN junction is fabricated. A PN junction is fabricated by special techniques, let me write complete, by special techniques, and some of them are, they are known either by growing, a channel is grown, and another is called, suppose, alloying. Another method is called the alloying, in order to make a PN junction. And diffusion is also there, a method of diffusion is there. As I said, what I mean by saying this, that it is not like this, you take a p-type material and an n-type material and join this and a PN junction is formed, although it is shown in this way only. One of the simplest methods, suppose I tell you it is about this, although it is beyond the scope of this, I say it is alloying. That is how you allow. By alloying, what you take, that you take n-type material, for example, this you take a n-type substrate here, this is an n-type substrate here. Simply, it can be a germanium or a silicon, and you add a donor impurity. Suppose I say that you indium here, this indium, all right, and it is a very high temperature is given here, about, I can say that, suppose it is up to 500 degrees centigrade. Now of course what will happen after this will be in a molten state. You have this pure germanium or a silicon here, n-type germanium or a silicon here, and now this will be in a molten state. I can say this indium will be in molten state, it will melt it. This will melt at such high temperature. If I apply a very high temperature here, this will be melted, and accordingly what will happen, that you will have, I can make it like this, that in spite of this complete, you will have this is your indium, this is n-type germanium here, and there's a p-type. If you see, a p-type is formed here. So this overall, a junction is formed between p-type and n-type. This is called p-n junction here. So this is a p-n junction all about, although this is not part of a syllabus, but I mean to say that it is not simply you take a p-type metal and n-type metal, simply join it, it becomes a p-n junction. It is not like this. A complete metallurgical process is there. A complete fabrication or a metallurgical process is there in order to form this p-n junction. So if you see how I saw the schematic of this, that you have a p-type here. Overall, this is here. This is how it is. On one side you have, this is P and a N is formed here, and this is called a junction. This is called a junction. So now if I define this, now this one of this part is called a P layer. This layer is called a P layer, and this is called N layer. If I talk about this one, this is called N layer. Now if I take some ohmic contacts from here, and if I take out two leads from here, one lead is this and another conducting lead, there is a ohmic contact here, and another lead is this. So the lead or the terminal, which is connected to this P side is called an anode. This is called anode, and this is called a cathode. That is the terminal which is connected to the N layer. There are two layers, P and N, and this is called a junction. This is called a junction. So if I define it now completely, now this is called a PN junction diode. If I take, it has two electrodes here, one is anode and the other is cathode. So this is called a PN junction diode. Now if I define this, what is this, a PN junction? Simply calling this was a PN junction, and now if I call that, what is a PN junction diode also at the same time? What do you mean by PN junction diode? Of course it is formed by combining a P type and an N type, of course. And if I take out these two leads from here, one is called the anode and the other is called cathode, the two layers are here, one junction. So if I define this, that this is nothing, it is simply two layer and one junction. It is a two layer and one junction device formed by combining this. So when I talk about PN junction diode, it has two layers. Two layers. And the two layers are what? It is the P layer and the N layer. When we'll discuss transistor, it is three layer and two junction. And this is one junction here. Two layers and one junction. So this PN junction diode is a two layers and one junction semiconductor device formed by combining a P-type semiconductor having donor impurity and an N-type semiconductor having acceptor impurity in very close contact. So I hope that this is clear to you. Now these two layers, one is called the P layer, the other is called the N layer. And if I talk about the symbol of this, PN junction diode, symbol of PN junction diode. If I look at the symbol of this PN junction diode, what is the symbol of this PN junction diode? You have this P layer, this is N layer. So two layers. This I draw a triangle here. Look at the symbol here. The symbol of this is shown by a triangle, and one of the vertex I draw a line here, and these are the two terminals. This is called the anode of this, and this is called the cathode, and this is representing the PN junction. This junction is represented by here. So this line, it is representing cathode, this is anode. You have a junction here, of course anode, I show this with a positive sign, and this is a negative sign. I hope that this PN junction, in general, basics of this PN junction is clear to you. The symbol of this PN junction is clear to you. Now let's talk about the formation of depletion layer. Next I'll discuss what do you mean by depletion layer. in PN junction diode. How depletion layer is formed. Or I'll talk about the same thing, open circuited PN junction diode. Now what happens that you have this is a PN junction, for example. This is a PN junction here. On one side, suppose I say that this is P side, this is P layer, and this is N layer. Open circuited means it is not connected to any battery. This is open circuit. It is no external source is not connected to this. When this comes out of the factory, what happens? Now this P layer, remember that this P layer is formed by doping the semiconductor with a acceptor type impurity, and N layer is formed by doping a semiconductor with donor type impurity. So when I talk about the P type semiconductor, see how P type is formed. If you remember, I told you this P type semiconductor is formed. You have a germanium, a pure semiconductor, and you add a donor impurity here. When you add donor impurity, every donor impurity releases an electron. Every donor impurity, an electron, and of course this donor atom is no more a donor atom, it becomes a positive donor ion. A positive donor ion. So it is very clear that initially it had some intrinsic concentration was there, some number of electrons and holes were there, but every donor impurity has released its fifth electron and becomes a positive donor ion. So if I look at the P side, if I look at the N side, at N side you will have a positive donor ion. A positive donor ion is, and of course every donor ion is releasing an electron. Similarly here, next donor atom, Nd plus. This is Nd plus. Another Nd plus. Another Nd plus here, and of course every Nd plus releases an electron here. I hope that this is clear to you. Now I am not writing Nd plus, I am showing this by a blue pen, that here you have this. These are donor ions. These are donor ions here, and every donor ion is releasing an electron here. Let me show you the red color. Every donor ion is releasing a electron. Has released an electron. Similarly, here you have these donor ions, positive donor ions of course, and with the release of an electron here. So here you have majority of electrons as compared to holes. Of course in intrinsic electrons and holes were there. Now let's talk about the acceptor, this P side. How P type is made? P type is made, you have a pure semiconductor, it is doped with acceptor impurity, it accepts an electron and becomes Na negative, and with the release of a positive hole. Every acceptor impurity. Third, it is a trivalent impurity. This Na is trivalent impurity. This trivalent impurity accepts an electron, becomes a negative ion and release of a hole. So this P type, P type, if you see that, look at this P type, what it does, it becomes a negative ion. This, let me show negative with red color only. It becomes a negative ion, that I am saying Na negative. Na negative. Another one, this is Na negative. Acceptor, Na negative, and every acceptor atom releases a hole. It is releasing a hole here. Similarly, now I am showing this by negative ions. These are negative ions. These are negative acceptor ions. Remember that. These are negative acceptor ions, and every acceptor ion releases a hole. Here. Let me show another ions. These are negative ions here. These are negative ions here, minus, 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 minus. These are negative ions, and every ion, acceptor ion, releases a hole here. So, or it accepts electrons from the system and releases. So this is how we try to understand that this is how a PN junction would have been formed. It is formed in this way. Now, apart from this, of course, this will have a intrinsic concentration also. Say, this is the, I am showing this by intrinsic concentration. These green ones are the intrinsic, electrons and holes. Electrons as well as holes. These are intrinsic concentration. This is intrinsic concentration. Similarly, here you have this intrinsic concentration is there. Means when it was pure. In pure, you had some electrons and holes, and of course, it is called the intrinsic concentration. But we are interested in this. Now, what happens if there is a concentration gradient? Means non-uniform, if the let's talk this way, that if there is a non-uniform distribution of electrons and holes, so these electrons and holes will diffuse from higher concentration to lower concentration, so a diffusion will take place. These charges they'll diffuse. It means what will happen, that these electrons, let's talk about near the junction. Near the junction, what is happening, that this electron moves towards this side, or I say this hole is moving towards this side due to uneven distribution of electrons and holes from higher concentration to lower concentration, or I say this is moving towards this side and this is moving towards this side. Now when they move towards this side, what will happen, that these electrons and holes, they recombine. They simply recombination. This is recombination of these electrons and holes is there till an equilibrium is maintained. Now what will happen, look at this, near the junction, the resultant of this, if you see that near the junction, this is your PN junction, this is P side and this is N side. Of course, here you have, on this side you have negative ions, acceptor ions, negative acceptor ions, negative acceptor ions, along with the positive holes here, along with the positive holes here. And similarly on this side you have positive donor ions. These are positive donor ions, and every donor ion, it releases an electron. So along with it, the electrons are associated with this. The same figure as it is here, along with intrinsic concentration. Now what happens, that near the junction, these electrons and holes, they recombine and leaving behind here, if you see that these are leaving behind here only these negative ions, and on this side only this positive ions. Only this positive ions. Remember that the current flows due to the flow of these electrons and holes. Now these ions, if you see that these ions, these positive ions, they obstruct in the flow of these electrons and holes, which constitute a current in the external circuit. And this region is, this layer, this particular layer is called the depletion layer. This layer is called the depletion layer, or this region is also called the space charge region. Depletion region means this, what this region has done, it has depleted the charge carriers from here. Deplete means to finish off. So it has depleted of the charge carriers, so, or the movable charge carriers. Remember that these are immovable ions. These are heavy ions. The current is constituted because of these electrons or these holes only. So this charge region, this ionic charges, these positive and negative ions here, they are obstructing these electrons. So this layer is called a depletion layer, and of course an internal battery is created here. I can say a positive and a negative, an internal kind of electric field is developed, and this potential is called the, suppose I say this, I represent this by VB. This potential VB is called a barrier potential. Why? Because it is acting as a barrier to the flow of these electrons and holes. They are acting as a barrier in order to that, as a barrier, so that these electrons and holes, they are not able to cross this junction. Remember that current flows in the external circuit only when these electrons and holes, they cross the junction. So they are acting as an obstacle. It is acting as a barrier. So this potential is also known as barrier potential. I'll continue with this topic in the next lecture. So thanks for the time being.